Good morning, everyone. Thank you for having me here. And my name is Yang. I'm just doing my Marie Curie Fellowship in Microelectronics Research Unit in University of Oulu. My supervisor is Dr. Aalto. I've done something about single energy harvesting and single energy source harvesting before, based on piezoelectric materials. But it's not the same as the one Yari just presented. It's based on the cantilever-based. I will talk it in detail. And now I just transferred to the multi-type energy harvesting, which is different from just the simple combination of different devices together. We put everything on the same chip at the same time, and we connect energy using different principles. And I'm just doing everything on the same material. Ultimately, it comes from the same principle, actually. So I'm going to talk about something about what I've done before, and mainly about what I'm doing now, more energy harvesting. If you got any question or if you don't understand anything, just interrupt me. I can explain more and answer your questions. Probably everybody has known that energy harvesting means a system rather than a single material or a circuitry or some end user. We consider those end users as a conventional power supply. It can be like batteries, it can be some mains powers coming from fossil fuel power stations. But for the energy harvesting, we got some ambient energy. It can be from the sunlight, it can be from the heat around us, heat from the engine, and it can be fluidic. It can be from the wind, from the water flow, or even from the raindrop, and also mechanical energy, which is probably the most widespread energy around us. And this kind of energy harvested by the energy harvester, then we somehow manage this kind of power and regulate them, rectify them, and it can be stored into the energy storage, or it can be directly used by the end user. As we all know that the solar panels and the wind turbines are getting very successful nowadays, and they generate a huge amount of market and profits every year around the world. And also, I think you all know very well about the thermoelectric energy harvesting, and it starts to show some practical usage. So I'm not talking about much about thermoelectric, which is all you well know. So let's have a look at the energy requirement of the practical devices in the industry. We come from like microwatt level, which can be used in the medicine, and it means micro electromechanical system or nano electromechanical system. And if you go higher than a milliwatt, we can use them for some industrial sensors, or even some low power consumption wearable smart devices. And if we go into like 100 milliwatts, we can use it for mobile phones or TV remote. And if we want to power larger devices, we need actually at least 1 watt of the power. So where we are now is here. What I was doing before for piezoelectric and harvesting was actually around this level, energy level. Actually, to the state of the art, we are also in this level. Of course, depends on different materials you select, different structures you build up, and you can actually harvest different levels of energy. I think the triboelectric, thermoelectric, and the photovoltaic effect are probably the most capable so far. So they can do a quite large range of energy harvesting depending on the device size, the surface size, etc. But actually, the piezoelectric energy harvesting, the advantages for them is that they are very compact. And you can just use one piece of material and you just bend it and you press it, it will generate. There's no moving part. It's different from the electrodynamic energy harvester, where you need actually two moving parts moving relevant to each other. And also piezoelectric energy harvesters can generate higher voltage than other principles, like electromagnetic. The main drawback of the electromagnetic effect is the very low voltage. Yeah, I'm going to skip this because Yara has presented a lot of this industrial application, and also I think this piezoelectric energy harvesting area is more or less stepping out from the laboratory to the industry nowadays. And it got some issues, but these issues are being solved, and it's getting better and better. There is actually an industrial product already. Well, I think this is the best one in commercial sectors. And it's coming from the meat. It's called the Vulture PPA products. So it's cantilever-based energy harvester. So it contains different layers. So there's one piezoelectric layer here, and they got some protection layers and some electrodes. So basically the simplest structure we can have for cantilever. So it will bend up and down and collect this mechanical energy or kinetic energy, whatever you call it. But these applications will be based on the harmonic vibration, which is quite periodic, and get definitely or nearly the same peak value at every time, every cycle. If we have a look at it, because we are doing quite good for our shoe-based energy harvesting as well. You can see even for the best industrial case, we can only just get up to like 10 or 12 megawatt output. But it's actually depends on the tip mass you attach to it, and also the frequency. You need to go to very high frequency and a very heavy tip mass, or relatively heavy tip mass compared to the size, and then you can get to the highest number of output. But what I was always thinking that will this be, or this kind of dream, be kind of next big thing or a disappointment? So people are always dreaming. I think people was dreaming from like since 10 years ago that someday we can charge these mobile phones by just random movement of people's daily life. And when we take on the train, on the metro, and the bus, and when we go some exercise and do some workout, and even we are just tipping on the keyboard, and our body are moving, and we collect this energy, and we charge our smart devices like smartphones. But nowadays, it seems that the current technology can't fulfill this requirement. The problem, I think, is because of the random movement. People are doing a lot of research on the random vibration modeling, devices, materials, structures, a lot of these things. But currently, nothing is going beyond this level to fulfill this practical requirement. I've experienced kind of a project, development project for these smart watches, smart band actually. Yeah, it can act as a kind of your exercise monitor or calorie burning monitor. And it's based on this cantilever structure. If you have a look at this principle, so actually we have two layers of, we have 4 cantilevers opposite to each other. You can see it here. 1, 2, 3, 4. And actually for half of this, you can see we use this kind of the holder of the earphone of this part. We modified this part, so this part can be moving, and it will move up and down, and it will trigger the cantilever actually vibrating in its eigenfrequency. We lose some flexibility of the material, the cantilever, which, well, I think most people are making effort to the flexibility of this kind of harvester, but actually we get even better results from this non-flexible structure. The reason is because we use the property of the material is very good. It's much better than the flexible materials. So that's the result we got. We get some very practical daily real measurements with some volunteers. So that's the average output we can get from people's daily life. So the short interval here means, I will explain it later, means that just the largest peak we get from this movement. And the 10 seconds means the 10 seconds root mean square, which means a stable result, which we can rely on. Actually. So that means the real output power. This means the ideal, the maximum output. So probably you can get the highest power from hand clapping, and probably you can expect it because there's the largest energy in that occasion. That's how the output looks like. If we pick out just the one movement, you can see that when it starts to trigger the cantilevers, it gets the largest output, and then it's actually damping to zero to the end. So it's in a very short period. This is based on rounding data. So we have 4 cantilevers, so there are 4 outputs. Yes, as I said, people are developing flexible energy harvesters based on random movement. But actually, there are a lot of options. Actually, if we have a look at this first, if we compare the literature, if we compare the energy density, or let's not talk about our recent developments. It's a kind of boost, but if we consider all of this, either for ceramics, we don't have flexibility, but we have the highest output, peak output, or we have the piezo-polymers or some stretchable nanofibers. We have the flexibility, but we don't have the advance for the output. And actually, the unit power density or the unit RMS of the power is actually staying on the same level. And it's okay to power some industrial sensors. Like we need some periodic data transmitting and receiving, but it's not functioning, every second, every minute like this. Yeah, it's okay to apply this, but actually, it's not quite enough to charge our devices. There's still a big gap. So yeah, so this is a kind of a relationship between different materials. Sometimes you get a very high peak output power for the ceramics, but you lose a lot of flexibility and non-linearity. Non-linearity means the frequency range you can actually run the device. And also you get some modest options, but you still get these results. The reason is there's no stable energy input because people are not moving every day, every second. And sometimes we sleep, sometimes we sit down and stay quiet. So there's no energy at all. So there's a big problem for random movement energy harvesting. So a short summary for what I've done before for physical energy harvesting. Because it's my background, it's my PhD thesis, I really dream that someday it can come true that we use this to power a lot of devices. But now it seems that it's very promising for the wireless sensor networks, where sensors require not so much energy, but the reliability or the lifespan is the most important. So I started to think what we can do beyond this. The idea of harvest different energies from different sources in the same module. This idea is not new because a lot of people have started doing it. But what I think is that if we combine different devices together, we will get actually the size larger and larger. Yeah, you combine another thing, you'll get larger again, another thing even larger. So what I'm thinking that we can do the same thing on the same material. So there's a kind of opportunity. We call it the perovskite structure. Maybe some of you know it well. There are actually two, let's say, types of causes. Firstly, we call it the simple perovskite, which is a ABO3 structure. You can have you have the A side and the B side, and also oxygen octahedra. And if you see it from the side, it will generate this spontaneous polarization inside the unit cell. These kind of structures are used widely as piezoelectric materials and also pyroelectric materials. Pyroelectric means that we transfer the temperature fluctuation into electricity, or vice versa. And recently, from 2010, I would say, there was a structure called the organic halide structure. And it's very promising to be used as photovoltaic material. So let's have a look at this photovoltaic, perovskite photovoltaic. You see the development is actually boosting to itself. And in comparison, the silicon-based and also the dye-based, they stayed for the same level for quite a long time, over a decade. So what we can do now is that, can we combine these two structures? Or can we combine the two functions together to make something really different? So let's have a look at what people have done before. The simple hybrid energy harvester, combination of different components. People use like the traditional solar cell plus thermoelectric energy harvester, which is also an energy harvester, I guess, to collect the solar energy and thermal energy. And also people use this kind of zinc oxide to harvest solar energy, and also the dye-based solar cell to harvest the solar energy, and also the zinc oxide to harvest the mechanical energy. And also people developed this structure using this PVDF to simultaneously harvest the piezoelectric and pyroelectric energy, and also use this zinc oxide, actually nano arrays, I guess, for the photovoltaic effect. But you can see all of these are just combinations of different things, and it generates good results. You can see this add-on effect. So when we have the light and when we have the temperature fluctuation, then you can get this add-on energy. That's the general idea or general target of this development. But sometimes it can be redundant. The size can be bigger and bigger. If you don't worry about the size limit, that's fine. But in my experience, that most of our applications will have a very compact, very small size for the energy sector, actually practically. So what I was doing first to check this ABO3 based structure to see if it has any promising or possible theoretical principle to do anything. So I got some results published on the Applied Physics Letters, and we can see for other traditional materials, we can see for piezoelectric, photovoltaic perovskites, they get some very good piezoelectric coefficient and also very good pyroelectric coefficient, but the band gap is terrible. We can't use them for visible or sunlight harvesting. And also for this, the band gap is good, But actually, this is actually not investigated. It's actually controversial. People don't understand now whether it's real ferroelectric material, and it sometimes can exhibit some piezoelectric effect, but people are worried that it's just because of the charges accumulated on surfaces. It's not the real internal ferroelectric domain stitching. So I went to a relatively safer way to apply this material with an oxygen vacancy in it. So actually, with the combination of the nickel and oxygen vacancy, you can elevate the electric state inside the material. And also, we hope to remain some of the piezoelectric and paraelectric coefficients. It's the very first preliminary results, but actually it draws a lot of attention. This is not the paper, it's just the press release published by the publisher, and a lot of websites has reposted it or cited it. But we are ongoing actually, we are doing much better. If we think about how we can develop this material further from that point, for energy harvesting, piezoelectric and pyroelectric energy harvesting, we need very large polarization. So we need strong ferroelectric material. And also for the photovoltaic energy harvesting, we need around just a 1.4 electron volt in order to effectively use the sunlight, the photon energy in sunlight. So actually, now we are here. We get conventional piezoelectrics, but the band gap is very large. It's like 3 or 4 electron volts. People done some band gap engineering by some doping, but it's not so helpful. The narrowest band gap before my results was like 2.5 or around 2.3 for business far right. It's still not enough. And we have these organic hydrogen perovskites, but actually, in principle, we can just increase the asymmetry of the unit cells and increase its ferroelectric response. But actually now it's controversial. It's more risky to go through this route, I think, because the materials itself is difficult to make and it's difficult to control, so it's not well studied. But actually, fortunately, I get something out from this simple APO3 structure. It's actually based on KNN. KNN is a very widely used lead-free piezoelectric material nowadays. Some company, I think in somewhere we already have it practically, the KNN, but I'm not so sure. But yes, KNN is the most researched lead-free piezoelectric position. And we use the same principle to introduce some oxygen vacancies here. But the amount is very, very small. It's just like the oxygen vacancy concentration is just like 0.17%. But we got very promising results, very promising. If we have a look at the D33, we got around 100 D33. And also we have a band gap of 1.6 electron volt. This is near the smallest photon energy in the sunlight. It's around red spectrum. This is the pyroelectric response. We add kind of a temperature fluctuation, and we get the pyroelectric current coming out. But if we just compare the individual properties, we can see this is pure KNN. Well, by the way, we need KNN because we don't want the lead in this PCT. And people, this is a kind of a large research area in the world. But anyway, the KNN can be the next piezoelectric material to be practically used instead of PCT. So I just compare with it. This is my material, this is pure KN. We can see piezoelectric coefficient, similar, very similar. Pyroelectric coefficient, very similar. And band gap, very promising for the new material. So it's, for KN, it's impossible to harvest any sunlight. But with this material, it's possible. It's been possible. And if you compare to the very first trial we've ever made, and it's a big improvement in terms of these two properties, and along with the very similar band gap range. So that's the response of this material. We use the halogen. The frequency ranges around, it's like from the infrared to the purple, I guess. And the deuterium is from the purple to the ultraviolet. And we get similar levels of these two frequency range. That means we can have an effective usage of the visible part of the sunlight. So if we apply, for example, if we apply it with pyroelectric effect and photovoltaic effect at the same time, under this kind of white light, we generate this level of energy, which is photovoltaic photo energy, photocurrent. And in the dark, we generate this pyroelectric response. But actually, with this white light and also this temperature fluctuation, we get exactly the add-on of these two energies. So that means they are not interacting with each other, and they perform independently, relatively. And also, if we have a look at this all three energy response, from the dark we have this. If we have a white light, it generates some level of energy. And also if we have some heat in, it will generate another level of energy, which is add-on of these two energies. And also we impact the material to add some mechanical energy. It will generate this piezoelectric response without any, compromise or a sacrifice of this total energy. So the highest energy can go here. Yeah, it go downside is just because it's an AC signal. We didn't rectify it, so it goes here. But you can see the highest level is actually larger than here. I got a video finally to show. Well, this video is the signal comes from this small sample, it's a ceramic disc. But don't expect you see very large, current, because this is not the most effective way to collect energy. It's inefficient. It's just a demonstration of the material. This is not a device. So, but you can see the principle actually.
I think you already kind of had the play button there, so if you try to move your mouse. Yeah.
Okay, so the sample is here. Yeah, so we turn off the light. We just use this table lamp, desk lamp, to introduce the light energy, and we get some level of the current. And also we turn on this hair dryer, which is a very common heat source. Yeah, because this is for demonstration, we use the most common energy ever in the world. And we applied some impact on the material, and you can see the response. It's like typical piezoelectric response. And then do it reversely, and the signal will be reversed. And now the signal goes to 0. Yes, so I think that's all of my presentation. From my research, I feel some hope for charging our mobile phones in the future, but it's still a long way to go. It's just a very initial material. We need to do a lot of things, and also we know that pyroelectric is not the strongest thermocouple method ever in the world. And also, piezoelectric, we need to do more works on piezoelectrics only in terms of the structure and the circuitry. Also, the circuitry, power management circuit is also important. Yeah, so some future works are definitely do more on the material and also do something on the device to see its feasibility really. And I acknowledge this my sponsor. Mary Curie Fellowship, and also strongest thanks to my colleagues Duomo and Yanni and Jaco for helping me generate some data of my papers. And also Pavel Topel is my previous colleague coming from Central European Institute of Technology in Czech Republic. I worked there for like 1.5 years. And also my previous my PhD institute at the University of Birmingham. Some of the results in this slide come from that period as well. And yes, if you got interested, you can actually Google me, and I got a personal site, and you can also send me emails if you got interesting questions or comments. Yes, that's all.
Okay, thank you. Let's harvest some energy for Jari and Jan.